Metal organic frameworks, groundbreaking or gimmick? That's what I will be looking at today on Science Spotlight number 3, Metal Organic Frameworks, or MOFs. I'm Dr. Mark Williamson for Transcend in the Research Design Compliance and Data Management Core. Let's get into this. What are MOFs? Well, a good place to start is a recent news article called Chemistry's Super Sponges Finally Hit the Market about metal organic frameworks and their use in the commercial market. So, metal organic frameworks, or MOFs, are powdery solids with a scaffold-like molecular structure, making them incredibly porous. And this feature makes them potentially useful for things. So, for example, this is like the chemical structure of DUT60, which actually has the biggest internal surface area of a MOF, and so you can put a lot inside. Here's a picture here of what they look like, this white kind of powdery solid. So, at the molecular level, MOFs have a repeating structure built from the two big things where the name comes from, metallic ions, and then linked by rod-like carbon-based molecules. That's the organic molecule. So that's why they're a framework made of metals and organic molecules. Metal organic framework. So because you can have a lot of different kinds of metals, a lot of different kinds of carbon-based molecules, and put them together in different ways, you can have all sorts of varieties. That's why there's actually more than 10,000 different varieties of MOFs now. However, while they've been interesting for a while, they're expensive to create for anything other than sort of bespoke academic purposes. Making them on a bulk level for industrial applications hasn't really been feasible until fairly recently. Now, initially, an application target, to actually make them marketable, was for like hydrogen gas storage. That kind of fell by the wayside for a while. So now companies, the big idea is looking into using MOFs for CO2 capture, but also other things like water harvesting and filtering out toxic gases. In fact, the idea of storing hydrogen gas is even coming back into vogue. So that's a bit of an introduction. Let's turn now to the beginning. The first synthesis of a MOF came in 1989 and was talked about in the paper Infinite Polymeric Frameworks consisting of three-dimensionally linked rod-like segments. This is by Dr. Hoskins and Robson. They describe this as a new and potentially extensive class of solid polymeric materials with unprecedentedly and possibly useful properties may be afforded by linking together centers with either a tetrahedral or an octahedral array of valencies by rod-like connecting units. So that's where MOFs came into existence. So the idea is they're a regular array of cavities interconnected by windows. That's how they describe them in the paper. And some of the initial ideas for what they could be actually useful for is for molecular sieves with their applications given their ion exchange properties and uses because of their mechanical and electrical properties, and then just used as a catalyst. And so this is what the structure in that paper of the first MOF, and it was using carbon, nitrogen as sort of that organic molecules, but then it was copper was the metal used in this. But since then, there's many different metals and organic molecules. So to get a broader impact, here's a couple decent reviews of the field. The first one here, a review on contemporary metal organic framework materials. This is from 2016. Really goes over a lot of different things, including synthesis, the different ways you can synthesize them. You can do hydrothermal, microwave-assisted, ultrasonic, electrochemical, mechanochemical, diffusion-based, solvent evaporation, and ionothermal. And also walking through different applications, notably LEDs and sensors, gas storage, that comes up again, magnets, drug delivery, and catalysis. And some useful little pictures here. Of course, the right side one is just a diagram of the applications. The left side one of sort of how MOFs can be put together. You can have a metal ion, you can have this ligand, that organic molecule, and you can do it in all sorts of different orientations. Then this other article here from 2019, not as in-depth, but still has helpful material. Again, some nice microscopic pictures of representative MOFs. So that's useful to sort of visualize what they look on a not the atomic but the molecular level, and some applications that they kind of bring through: adsorption in aqueous solutions, so that's like biological compounds, antibiotics, toxic pollution, gas absorption. So again, talk about CO2. They even talk about radon, which will come up later, something I'm interested in. As catalysts, whether it's photo, electrical, or bio. As sensors, whether it's electrochemical, photoelectrochemical, or biological. Charge storage, so whether that's batteries, supercapacitors, or fuel cells. And then finally, drug delivery systems. So of note, I can't show it up here, don't have room, but two particularly really helpful tables from this review is table 1, which gives examples of typical MOF names and their composition, because MOFs kind of follow this more or less standard formula how they're named. And then table 2 is a selected applications of metal organic frameworks. So those are helpful tables if you want to look more into it. And the references, links to the references will be at the end here and in the description. So this 2019 review. So turning now to biomedicine, again, that drug delivery, etc. I found a decent 2012 review of metal organic frameworks in biomedicine, because that might be a useful application. So it goes over several different topics in this review, kind of starting with the need for or the use of bio-friendly metal organic frameworks you use in biomedicine. Talking especially about, you need to figure out them first, maybe do some computational methods, but then you're really going to, if you're going to use MOFs in biomedicine, you're going to need to do in vitro activity tests, to provide activity information about cytotoxicity, cell uptake, intracellular distribution, degradation, bypassing of biological barriers, and how cells and those nanoparticles of the MOFs will interact. And so really, it's an additional layer of sort of the chemistry of the MOFs, and then the biology of how that interacts. You also need to, figure out metabolism, degradation, excretion, etc. So they go through administrations, or how you actually formulate these MOFs, especially MOFs that maybe have drugs or can attach things and be useful in biomedicine. Coming up with the idea of like the bioactive MOFs. Then some of the specific applications I have in green here. So drug delivery, that's the big one. Actually, storage and delivery of gasotransmitter gases apparently took up a good part of it. The three they focus on was actually nitrous oxide, hydrogen sulfide, and carbon monoxide, which all have potential uses in the body. In fact, the body does produce them naturally in some circumstances. So that was an interesting addendum. To talk about biodegradability and stability of MOFs. Toxicity, that's obviously a big thing. You don't want to use a MOF in the body that is too toxic. And also for use as MOFs in diagnostics as a use in biomedicine, like MRIs, optical imaging, X-ray, computed tomography. And there's some helpful pictures. The top one here is actually using them, not even in the body, but like using them to create these nanostructured surfaces that can kill bacteria, so an antibacterial surface. Sort of the scheme here about how you look at the biodistribution of especially the metal in a MOFs and how the pathways might go and how it might get out of the body, as well as just a more general picture of what a biofriendly metallic organic framework. So you're going to have the MOF, you're going to have some sort of biomolecule that'll go in it, and then it needs to be released somehow. All right, let's turn to some specific applications that I thought might be useful to sort of walk through. First of all is actually in my neck of the woods from North Dakota State University, this article in 2022, expanding the library of metal organic frameworks for enzyme biomineralization, where Biomineralization is where enzymes actually co-crystallize within the MOFs, and so that can be useful for a lot of things. So this is a graphical abstract. The authors talk about how MOFs are advanced platforms for enzyme immobilization, and they can actually be entrapped via diffusion or co-crystallization. And one of the really interesting things is they were able to discover a combination of 5 metal ions and 2 ligands that can form biocomposites with 2 model enzymes differing in size and hydrophobicity. And so they're able to, again, have more MOFs for this enzyme biomineralization process. And a second research article, I thought I'd bring this up because that was the big trumpeting of that paper we started with about MOFs maybe being useful for carbon capture to make them industrially viable. So I thought I'd put it out here. This is from 2021, a scalable metal organic framework as a durable physisorbent for carbon dioxide capture. They were working with this MOF here, Calgary Framework 20 or CALF 20, which has physisorbtion, so it can actually physically capture and store carbon dioxide. So that was what it needed to do, and also they could synthesize this in a single step and could be scaled up for larger production, so making it potentially industrially viable. Now, another specific application, what I'm very interested in, and actually got me in the orbit of what MOFs are and what they might be used for, it's actually radon absorption. So radon is a naturally occurring radioactive gas, pools up in people's houses and can cause things like lung cancer. And so it'd be helpful to find better ways to absorb it, especially lower cost ways. So a research in 2019, screening metal organic frameworks for capturing radioactive gas, RN, radon in indoor air. They actually did that. They tested a whole bunch of different MOFs, I think like 23 or something, and they found that there was one of them in particular, ZIF-12, which was particularly good in absorbing radon. And going back to a paper they cite about actually how to make ZIF-12, this toluene-assisted synthesis of rho-type, zeolithic, et cetera, from 2030. There's essentially just one paragraph about how you synthesize ZIF-12 in toluene methanol solution. And I'm no chemist, but that doesn't look terribly awful to produce. So I think there's a lot of promise in using metallic organic frameworks in something like radon research. All right, well, we'll close kind of out here with a bit of a hint to the future. This is a archive article from 2025, System of Agentic AI for the Discovery of Metallic Organic Frameworks, because of course everything is AI now. And when you're looking at a huge space of potential combinations of MOFs, something like MOFs, you have thousands already, you have probably millions or trillions, billions, whatever, of possible combinations. It's useful to use AI for that. So they introduced Moffgen. It's a system of agentic AI comprising interconnected agents. So essentially it's a large language model that proposes novel MOF compositions. So the parts, there's a diffusion model that generates crystal structures, a quantum mechanical agents that optimize and filter candidates, and then a synthetic feasibility agents guided by expert rules of machine learning, a bunch of other sort of stuff papered on top as well. And you thought, okay, that's kind of fancy dancy, but where's the proof? Proof is in the pudding. And well, it actually turns out it's really interesting. They were able to validate this by their models here were able to propose 5 different MOFs. They call them AI dreamt MOFs or AI MOFs 1 through 5, and they're actually able to successfully synthesize these based on the recommendation. So there we go. There's some proof that this could be really helpful. So with that, that's an overview of metal organic frameworks or MOFs. Here's all the references and links found in the description to this video. Thanks for joining me. This is put on by Transcend, so check us out if you are interested in translational research in North Dakota. Have a great metal organic day.